Hi, welcome back to es346 Basic Thermodynamics. This is module 8.4 on open system exergy, and the sections in the textbook are 8.4 to 8.5. Here are the two learning outcomes for this module. At the end, you will understand the equation for exergy in an open system, and you'll be able to calculate the second law of efficiency for an open system. So what I want to do now is come up with the equation for the exergy of an open system. And we can actually do this fairly straightforward. So if I've got an open system, I have some material coming in with some enthalpy H1, and it's going to come out with some enthalpy H2. And for example, let's say it's generating some work. If it was generating work, we know the enthalpy needs to go down, so we know H2 is less than H1. And the amount of work it's generating is going to be the difference between those two enthalpy values. Now, this also could be coming in with a entropy that would be S1, and when it exits, it could exit with an exergy S2. Now, we know that if it was isentropic, the highest efficiency, S2 would be equal to S1, but if it's inefficient, S2 would be something greater than S1. So if it was somewhat irreversible, S2 will be greater than S1. What I kind of want to get at is, what is the change in exergy? So this fluid that's coming in with this enthalpy and entropy S1 is coming in with an exergy. And as it comes into this system, some of it is going into the work here. So it's going to remove some of that exergy into the work that we're generating. And then the rest will go ahead and flow out. Now, if this is irreversible, though, some exergy can get destroyed. And in fact, we saw that we could calculate that as T naught Sgen. So some of the exergy could be getting destroyed in here, and then the little bit that remains is going to come out and be the exergy that's at the outlet. And so we could go ahead and write an exergy balance and realize that our change in exergy is equal to H2 minus H1, because that's the amount of work, minus T naught S2 minus S1, which is the entropy that is generated. So this right over here is the change in exergy, and the symbol that the book uses is this phi. So it should be phi 2 minus phi 1. So instead of using x for open systems, the book uses symbol phi. So there's phi 1, and over here would be phi 2, the change in exergy. And we can think of exergy being simply, for an open system, defined as H minus T naught S. So let's go ahead and apply this concept to an open system. Here what I have is I have a turbine, got these inlet conditions and these outlet conditions, but it's not adiabatic. We have heat being lost at 300 kilowatts. And I want to calculate the second law of efficiency. Now, in the previous chapter, we calculated isentropic efficiency, but we could only do that if the system was insulated. Now, here we have a heat loss, so we can't do that type of analysis. But now we have this new tool with exergy, we can actually determine the second law of efficiency of this turbine here. So I'm going to go ahead and determine the inlet flow exergy, and that's equal to H1 minus T naught S1. So here's my environment temperature at 25 Celsius, or 298 Kelvin. And I'm going to go ahead and use this value of T and P onto the superheated tables to calculate this value, and that exergy going in is 1233.4 kilojoules. And then using these conditions here, that's going to be the outlet exergy, and that's 599.4 kilojoules. And so the total amount of work that this turbine could go ahead and generate, I can calculate. That would be the reversible work, and it's simply equal to the mass flow rate times that change in exergy, psi 1 going in, psi 2 going out. And if I put in my 8 kilograms per second and these two values here, I find out that it's 5072 kilowatts. So that tells me the maximum amount of work this turbine could generate would be 5072 kilowatts. But that doesn't mean that's the actual amount that it's generating, because I actually haven't even used this value. So we know that if we were to calculate the actual amount, I'm going to have to write my energy balance in there. So I would have the mass flow rate times enthalpy going in and now I have three things going out. I have Q, W, and a flow coming out. So M dot H2 minus Q minus W. I'll call it W actual, the actual amount of work. This is the reversible work, the total work I could have gotten. So if I write down those values, again, I hit these off the table. This is 2769.1 kilojoules per kilogram. H1 coming in equal to 3345 kilojoules per kilogram. We needed those when we calculated these as well. And so now I can go ahead and rearrange this to go ahead and solve for the actual work. And the actual work is equal to 4307 kilojoules. So putting in those values of enthalpy, my mass flow rate of 8, and my Q is equal to 300. So with this inlet conditions and this outlet conditions, I know the actual amount of work. Here's the total amount of work I could have gotten in the system, the reversible work. So let's calculate a second law efficiency. Well, that's going to be the actual work I get over the reversible work that I could have gotten for 4307 over 5072. And that's equal to 0.85 or 85%. So what that tells me is that this turbine is operating 85% efficiently. I could get another 15% out if it wasn't irreversible. And there's one source of irreversibility is clearly this heat being lost, right? If I just dumping this into 25, I could have went ahead and put some other heat engine in there as well and extracted a little bit of additional work. So this tool of second law efficiency is useful for systems that are not adiabatic in order to quantify how well they're operating relative to a reversible system.